All right, guys, so this formula here, this is Newton's law of cooling's formula, but this is the version that we're going to be using in all of our problems. Let's talk about some of the variables that are defined here. So this is very sciencey. They use a lot of subscripts, so be careful here, guys. It says T sub F is the final temperature of your product. So you have a temperature that you'd like to lower it down to. That's my ideal temperature. So like baking a cake, I might want it to cool down to 65 degrees because I want to frost it, things like that. All right, temperature of your surroundings. Right. Temperature of your surroundings is notated as T sub S, but sometimes in your worksheets that we're about to do, they call it T sub M, which means the temperature of the medium. So they use the word medium when it's a more technical experience, like at Dad's work, where they might do a submersion in a water bath or a chemical bath. Okay, so the medium would be the water in that case. We have a problem coming up, a really exciting one about a hard-boiled egg. Yeah, that one goes in a water bath. So they might use the word medium instead of surroundings. It's the same thing though. And then T sub naught is always the original, so in this case, original temperature. So the way these problems work out is I give you a set of information that's going to help you calculate what's called the constant of cooling. Depending on your situation, the constant of cooling is going to be different. So we have to do a little setup It's not little, actually. These problems take forever. So we got to do one setup to find the constant of cooling, and then we're going to use that constant of cooling to find an answer to a follow-up question. So these questions all have two parts. Keep that in mind. All right. So this one, we have, well, look at there, Mrs. Bruzo's coffee cup. It cooled from 92 degrees Celsius to 50 degrees Celsius. So this is my initial temperature. The 50 degrees Celsius is my final temperature, but for part one of my problem, okay? And then it says 12 minutes, so right there is your time. And then the room itself is 22 degrees Celsius, so this is the temperature of your surroundings or the temperature of your medium. Then there's a follow-up question. It says, how long will the coffee cup take to cool to 30 degrees Celsius? So this question right here, this is for part two. So don't use the 30 degrees Celsius quite yet. All right, here goes our setup. Part one, I'm going to do my work down here because I learned last hour that I write way too big. I already knew that though. All right, part one, we're going to use this equation and we're going to plug in everything we can figure out from the first part of the problem. So the final temperature, which was 50 degrees, for the first part of our coffee cup problem, 50 degrees, minus the temperature of your surroundings, which is 22, equals, and then a quantity, the initial temperature, which was 92, minus the temperature of your surroundings, which was 22. This is being multiplied by E, oops, not the right color, that's not an eraser, try again. Multiplied by E, and then up in the exponent of E, it says negative K times T. So write down a negative sign, and then I don't know K, but we do know that the time is 12 minutes, so I'm going to write down negative 12K. I need you to solve for K. So essentially, I'm asking you to solve an exponential equation where your variable is trapped up in the exponent. All right, here comes our algebra. Ready? Everyone have that written down? Okay, these are your notes, so I don't encourage lots of skipping around as far as where the numbers are coming from. So even though you want to take shortcuts, maybe now's not the time. Ready? 50 minus 22, isn't that 28? And then this is a 70 times e to the negative 12k. A little simplifying here. All right, before I do any logarithm work, I'm going to divide both sides by 70. And technically speaking, there's nothing wrong with just leaving this as a fraction, but you guys want to go ahead and just type that in for me? Is 0.4? Okay, well that's not too bad. If you get a really funky decimal, it's probably ideal that you not type in the decimal or write down the decimal and truncate it. All right, so you have 0.4 equals e to the negative 12k power. So now it's time for me to apply a logarithm. Would you like to use a common log or a natural log for this question? Natural would be beautiful. Look what's going to happen. All right, so on the left-hand side, you got something icky. Can you give me a decimal representation for the natural log of 0.4? I like how you just stare at me like I know this off the top of my head. I don't. It's something negative. Thank you. Because natural log of something smaller than 1 would be like the asymptote part of the logarithm. Yeah. All right, so these cancel and you get equals negative 12k drops down. So final step here, guys, you're going to divide both sides by negative 12. And you're going to get your constant of cooling to be roughly something. Should be small, yes. 0.076-ish? Okay, cool. So one thing to note is that your constant of cooling should always be a positive value because in the formula itself there is a built-in negative, and that's what allows your formula to keep cooling the temperature as it progresses through the domain, okay? It's a that was a label on it?
Like,
oh, jeepers.
Is there a label to that, or is that...
Yeah, no, there is, but like, I'd have to think really hard about that for a minute. Let's not worry about it. All right, so time to cool to 30 degrees. All right, we're finally ready for part 2 of this problem. You ready? You ready? Part 2 looks really, really similar to part 1, except this time you have a new final temperature. So your new T sub F is going to be, I already forgot, what was it? 30? All right, so your new final temperature is 30 degrees. You're going to use your K of 0.076, and this time, I don't know time. So I'm going to leave that as a variable, okay? So same formula, a little bit of a different setup though. I need to scroll up. 100 years ago, I had the formula up here. So remember, your final temperature is the beginning of the formula, and it just got changed to 30. So we're going to do 30 minus, I'm trying to keep my colors the same. All right, 30 minus 22.
Now it's 8.
Yeah. And then, see, you're just like psychic.
Yeah.
And then 92 minus 22. And then times E to the, there's a built-in negative sign in the formula. We have our K of 0.076. If you kept more decimal values than that, you're just going to be more accurate. And then times a mystery time amount, which I don't know. So the math is going to work out the same as far as the process, but since you have different values, you're going to get a different answer, of course. So yes, this is now an 8 equals 70 times e to the negative 0.076 t power. I'm going to have you divide both sides by 70 this time. So, well, it was still 70, but what is 8 divided by 70 as a decimal, please? Say it again. Okay. Equals this guy, and then once again, we're going to be applying a logarithm of what type? Natural would be brilliant. So now I am going to take a bit of a shortcut. I know that these are going to cancel out, and I know the natural log of 0.1143 is some disgusting number. The last thing we're going to have to do, if I think about my algebra, the last thing you do is divide by negative 0.076. So as far as like how you can take a few little shortcuts, because yes, these are annoying, that might be a possibility right there in your work. Can y'all type that for me? Make sure you close the logarithm after the decimal of 0.1143 and then divide by negative 0.076. And you get 28-ish, right? What'd you guys get exactly? Okay. So with rounding truncation, 28.54 minutes. So notice it wasn't like a how many more minutes question. It's just from the beginning of the problem. So if this says I was supposed to leave my coffee out for 28 minutes, I disagree. I don't know what kind of boiling coffee you have. Maybe you got one of those insulated cups or something. I don't know. My coffee's cold after like 5 minutes. I don't know. We'd have to calculate that. 9/5 times...
What are you...
To go from Celsius to Fahrenheit.
It's 1.8.
Times the quantity of Celsius plus?
No, okay. It's Celsius.
Yeah.
Times 1.8.
Minus 30 plus 32. Okay. That. Yeah, that makes sense. Because whenever you're like overseas, they're like, just double it and add 30. And I'm like, yeah, that's kind of close. Gosh, that's practically boiling. What kind of coffee you making? My goodness.
Away from boiling.
That is crazy. My goodness. All right. Well, I guess I'm making my coffee wrong, guys. I don't know. Okay, so another problem that's close and near and dear to my heart, the thing I like second most beyond coffee, This cake. I love baking cake. Now, I got a lot of problems with this cake problem. First of all, the very end of the question, how long will it take the cake to cool down to 90 degrees? Why do you care?
It'll be to 90 degrees before we get done calculating.
Well, that's the funny part. By the time you end up calculating it, it'll be cool. Now, I got a problem as a baker. Why do I care if the cake's 90 degrees? What are you going to do at 90 degrees? You're going to frost it? What's going to happen?
It's gonna melt.
It's going to melt right off.
Yeah,
You're just going to have like a sugary glazed loaf of bread at the end of this. So
that's
you need to revisit this question, baker. You need to think about this.
That's how John lost math.
Really? His stuff just came right off? He didn't use the blast chiller?
No, they didn't blast chill.
What? That was
No,
so...
she didn't. I couldn't remember her name, so I just made up.
You have to use the blast
No,
chiller on
she didn't
those.
have enough time, so she didn't blast chill it.
Ugh.
Yeah, she had like 3 seconds or 3 minutes left. And it's not enough time
You
to
know,
blast
you
chill
know,
or frost it.
you know, if they went into that competition knowing exactly how long to blast chill, they would have won.
Yeah.
Just saying. They would have won.
Yeah.
Little pre-calc calculation on
But
your
yeah,
part, people.
It's really
All right.
so sad.
All right, so a cake is removed in an oven of 350 degrees Fahrenheit, cools to 120 after 20 minutes, room temperature 65. Why you keep your house so cold? Okay, how long will it take to cool to 90 degrees? So once again, this last question here, this is for the second part. Don't use this information yet. All right, here we go. We have the initial temperature of 350, the original final temperature of 120, and then that's 20 minutes, so T equals 20. And then the temperature of your surroundings is 65 degrees. So for part one, which is going to allow us to find the constant of cooling for this cake, we got to set it all up and find K. Here we go. So temperature final was 120 minus the surroundings, which was 65, and then equals the quantity of 350 minus 65. And then you're multiplying that by e to the negative t times k, so negative 20k power. All right, little simplification, and again, these are your notes, so it doesn't help to skip all your steps on your calculator, and you got to write something down. So 120 minus 65 is 55, right? And then this is 285. E to the negative 20k power. Yeah. So divide by 285. I'll go ahead and take a decimal from you here just so I don't have to keep writing down the fraction. What's 55 divided by 285? And I'll be honest, guys, when I'm going to do something really gross on my paper right now. When I'm doing this on homework or keying it for you guys, what I do on this step is I just go, and then I sneak in a natural log right here and here. And then what's the last thing I'm going to have to do? I'm going to divide by negative 20. So like when you look at my work, that's what it looks like. But that makes a lot of sense to me, right? But that's not going to make any sense to our friends who are just looking at this. So can you guys tell me, yeah, was that the 55 divided by 285? That's the number I'm looking for. Thank you. So now, on both sides, we should apply the natural logarithm. I know. Like, guys, I know you all think you're lazy. You got nothing on me. I promise you. All right, so you're... Oh, yeah. All right, natural log of that decimal that Taylor gave me. Now, if you were worried about truncation and you want a really accurate answer for your cake, you just would type the natural log of 55 divided by 285 or use your answer key on your calculator, you know. So what does this come out to, by the way? This natural log part. Thank you. And then the negative 20k drop down. So finally, we're going to divide both sides by negative 20. And you do get a positive k value, which we're supposed to have. Is it like 0.08-ish? Thank you. And then it's not real specific about like where to round. So if it doesn't clearly tell you where to round, at least give me 2 decimal values, or 2 points after the 2 values after the decimal point. The more accurate you are, the better your cake problem will come out to. All right, so let's talk about part 2. So part 2 here, we have a new final temperature of 90. Well, make it work. I should have warned you that we had 2 parts. Oh, I did. All right, 90 minus 65 equals the quantity of 350 minus 65. Now, the other thing that changes on this setup is this time you're going to use the constant of cooling you just found, but the T is going to be our variable. So you have a negative, oh my gosh, I wrote too big, 0.0823 times T. Alrighty, what do we have here? 25 equals 285. That was Mrs. Hoffbauer. It's not a ghost. It was Hoffbauer. Okay, I'm going to need some decimals from y'all, so at least our work looks a little pretty. What's 25 divided by 285 roughly? I thought it was 0.4545 something.
Well, that
No?
can't be because
What?
it has to be
Oh, I'm
smaller
sorry.
than-
Yes, ignore me. Yes, go ahead. Okay, what is it? Sorry, I dismissed. Wait. Not. Yeah? Yeah, okay. I was looking at my key, which I should never do. And when I originally keyed this worksheet, I always interpreted the question to say, like, how many more minutes would it take to cool? Because, like, your cake has already been cooling, you know? So I kept answering them that way. So my initial temperature of, like, 350, I changed to, say, 120. So it's okay. I fixed all my keys from that previous year, like 3 years ago when I initially keyed this for your homework. So every time these questions come up for you guys, we always want you to go back to the initial, like I took it out of the oven temperature. Don't say like how many more minutes. I just want to know how many minutes from the beginning of the problem. Anyways, I digress. You guys got to apply some logarithms for me. I'm getting lazy. So this time I would like you guys to not only apply the natural logarithm, but also remember that you have to divide by negative 0.0823.
We should do this while it's baking.
Right, and then it's probably done, like you said.
Great way to pass time.
I say yes. Is it about 30 minutes? Is it somewhere?
Is that what you got?
Yeah, and it's, I mean, we're baking a cake, so it's not like, you know, you need to be accurate to the 10,000th place or anything, right? So, real close to 30 minutes, huh?
36. Wait, 36 seconds. 29 minutes.
Jeez. But, you know what, like I said, it's a moot point because who cares? What are you going to do with your cake now? You can't even eat it. It's 90 degrees. Well, I guess you could eat it. Then you're just eating bread. Why would you want to do that?
What?
Cake with no frosting is not cake.
You
Yes.
are wrong.
Yes.
You are wrong.
No.
Cake batter and bread dough are two very different things.
Cake with no frosting is a waste of your time. I'm just going to throw that out there. Prove me I'm wrong. Yes. Yes. What kind of cake are you eating that there's no...
I'm just angel food cake.
You should put frosting on it.
You're wrong.
Whether it be in the form
You
of
are-
strawberry glaze or chocolate frosting.
You are wrong.
Angel food cake.
Angel food cake. You put
Okay.
whipped cream on it and strawberries.
Well,
but you don't have to have those. It's amazing either way.
Daniel, I just don't agree.
You're wrong.
Okay. You should try angel food cake with fudge frosting on it, and then you can know that I'm right, Daniel. It's fine.
No.
I think you're right. Okay, so I want to talk about this function because this, for some reason, this really messes with kids, this half-life function and also the doubling time formula. And we haven't had a lot of examples in our notes, so I'm going to go ahead and do this one with you. Unfortunately, this one's already written for you, halfway at least. The formula is right here, where it says you take the initial amount, you multiply it by half, 0.5, and then it's x over h power, where x is the amount of time that's gone by, and h is the amount of time for the half-life. So when you have, in this case, a radioactive isotope, the half-life of radium-226 is 1,600 years. What that means is when 1,600 years passes, the amount that you have is going to be cut in half at that point. So they use this a lot for carbon dating, essentially. This isn't a carbon example, but it's the same idea. They use radioactive isotopes for a lot of things in science. So in this particular case, they have a 120 milligram sample. This is the initial amount, which they're calling P in the formula. Why is the base 0.5? I'm not meaning this to be a tricky question. Why is it 0.5? Because it's called a half-life. Yes, so you're using 0.5. What if it was a doubling time question? What would your base be? It would be a 2. Good. I don't know why. That really bothers kids on the test on Friday. Doubling time means 2. Y'all okay with that?
Everything has been backward.
Well, yeah.
So
okay. How much will remain after 4,000 years? Now, this clue right here, this is the amount of time that's going to go by. That's the x. And then earlier in the question, it told you that the recorded half-life for radium-226, so this is the h, is 1,600 years. So in your home screen of your calculator, you're going to set up 120 times 0.5 of 4,000 divided by 1,600. So this particular sample has gone through more than one of its half-lives. So it halved again, and it almost halved again. It's 2121. That's not something you should do mentally. Okay. And if you think about that, like it halved once, like the first 1,600 years it halved to 60, and then the next 1,600 years it halved to 30. So that was at 3,000 years, or 3,200 years, excuse me, and then it like partially reduced again. So 2121 makes sense. All right, how long until there'd be only 10 milligrams? Well, guys, you have enough algebra skills that you can solve this accurately. So the 10 milligrams is what we're going to throw in for the answer to the equation. And we're going to start with that same 120 milligram sample. And then this time, the amount of time, the x, is a variable, but it's still a half-life of 1,600 years. So I'm going to have you solve this, just like we always do with logarithms. But first, we're going to isolate the base. I don't know what decimal it is, but I know it's a 1/12. So this is a bit of a bummer, and I know the Newton's law stuff was kind of annoying because it was laborious, but at least you were able to use natural logarithms on ease, which was awesome. Here you don't really have that choice. I mean, you can use natural logarithm or a common log, but why is neither one going to be that exciting? Because you got a lot of work. Now nothing cancels. So your choice, natural log or common log? Okay, switch it up. Common. So you got a common log applied to both sides. And even though nothing cancels, what does happen is this exponent, ooh, I don't agree, comes down in front of that logarithm. So you've got the common log of 1/12, something gross, and it equals x over 1,600 times the common log of 0.5. And this is the moment in your math where you realize, yeah, it didn't matter which logarithm I used, because you got to solve for x. So I look at this problem as I need two things to move. I'm going to divide by the log of 0.5. And all of this happens on my calculator. You guys want to just tell me a decimal that comes out to, and I'll jot it down, although I don't want you to truncate it on your calculator at all. Okay, 3 point. Well, okay, I'm just going to do that. And then what's your last step to solve for x, y'all? Yeah, multiply by 1,600. So all of that can happen in one, maybe two steps on your calculator. Either way, I don't have an answer, so I need to know what you guys got. Okay. Years. So you're going to have to wait a while, I guess. Although, to be fair, I don't know when they got this, when they retrieved this sample. So there you go. Okay, cool beans. All right, take a look at worksheet 10. 10 is where your homework starts, so let's try to get as much of this done together as possible.
You should do an experiment.
Yeah?
Yeah.
Of what? Does it have to do with coffee?
No.
Oh.
It can, though. That's what you want.
That's where my passion lies, so.
C, what the effect is on this classroom
Uh-oh.
if
Yes.
you decide that homework is unnecessary and
That
you don't
is-
want to sign it.
That's false, and I will never have that. No. No and no.
I should go up for a second.
I was like, where's he going with this? It's going to be a classic moment of no. Okay, here on your worksheet 10.
Classic no.
So here's what you're assigned. 1 through 4. And then 6 through 8. Okay, so you might want to circle those. And then you're going to go, so not 5. And the answer is yes. The answer is everything but 5. Hofbauer took out the dreaded rabbit problem. All right. So number 1, man, I can't wait for you to answer number 1. It's a classic Newton's question. This is what Newton had in mind when he derived the formula. They're hard boiling an egg, y'all. I'm not going to do this one. I'm kidding. I don't really think he cares about that. Maybe he did.
Wait, why did he do it?
I don't know. We'd have to look that up.
I didn't know.
Yeah, no, I don't know. And frankly, he probably is accredited for it and shouldn't be, because that's usually how mathematicians worked back in the day. They were like celebrities and rock stars, so.
So it's
Yeah.
almost like a certain band making a song that a little band wrote.
Yeah.
Famous.
Yeah, I mean,
They got credit for it.
mathematicians, scientists, and physicists, like, obviously they're famous for a reason. They're brilliant and had really cool things going for them. But they had so many working underneath them. Like, they were scholars and educators, essentially, and oftentimes they get credit that they probably don't really deserve. And if, like, there's a lot of history and interesting stuff that goes on. I know in our Algebra 2 class we talked about, like, they essentially had math battles, which I think is kind of fascinating. That's how they earn their money. Like, they would
Like in the
tour,
Coliseum?
kind of. They would challenge each other to be like, I can do this better. And then they would present a problem and say, like, can you solve it? And then they could or could not. And they would battle each other. And they were like celebrities. They were like crazy famous and got a lot of money for it, right? So they would derive things and come up with formulas and keep them to their deathbed, like as a secret. And then they'd like whisper it to somebody, like the next round of mathematicians who was supposed to also keep it a secret, and then they wouldn't keep it a secret. It was hilarious. Like when you watch the history of the videos of it, like people have like researched their lives and what really went on behind the scenes is kind of crazy. And God forbid you were a woman mathematician, because y'all know what happened to the women mathematician, right?
Is that even a thing?
Uh-huh. They were murdered.
Oh, so no, it
Yes.
wasn't.
Well, they surely didn't get credit for anything. Like the most famous one now from back then was Hypatia. She's the most common name that they throw out there. And I believe Hypatia was either bludgeoned to death or stoned to death. I forget which, but she was murdered because they said she was a witch. Because how could such a silly little girl be so very smart? So if you were a smart girl, you had to kind of keep it under wraps. And Hypatia, I believe, was raised, I forgot who her father was, but very famous mathematician and philosopher father. She, like, under the tutelage of, again, I forget the names. But, like, they didn't believe that she could possibly be smart because she was a woman, so they killed her, like, at some point. Yeah, witchcraft, you know. It's rough times. Okay, so I'm going to let you guys do this problem on your own. Remember, these are 2-part questions, so you might want to save some space in your workspace where you have part 1 and part 2. In part 1, you're going to use 96 to be your initial temperature for the hard-boiled egg. And then 16 degrees Celsius is the temperature of the water, so that's the temperature of your surroundings. And then I hate when they do this 4 minutes later, so that's how they sneak in their time, and they wrote it as a word instead of a number, and it really bothers me. But 4 minutes is what you're going to plug in for time on the first part. And then they want your egg, the final temperature, for the initial part of the problem. It got down to 45 degrees Celsius. So then, part 2 of your problem, you're going to have a new final temperature of 20 degrees Celsius. Yeah, which makes sense because it comes out of boiling water, you know?
Water boils at 2.
Well, you use the truncated version of that formula. It's a little less than 2. It's 100 and, I don't know, something. It's 96 degrees Celsius is under boiling. because it's 100 degrees Celsius is boiling. So when you use the 1.8, like it's a little off. It's okay. It is about boiling is the answer to that. Yes. All right. So I'm going to let you guys do number 1. I can't wait to find out when your hard-boiled egg is ready. This is like need to know information, guys, right? Now this question is about death. So that really speaks to all of you, I'm sure. So notice in this question, they just went ahead and told you the constant of cooling for a human body because they know that. Like, this is not the first time someone has died, and they have research and calculations. Depending on what the temperature is of where the body is left, they can tell you how long it has been decomposing based on a few things, but this is one of them.
It just sits there, right? And doesn't cool off anymore.
Right, it will get to room temperature.
Equilibrium.
Right. So this one has not got there yet.
After it's reached that point, though, they can't tell how long.
They have
the
other
factors,
things, yes.
like,
blood coagulation and things come into play. It's pretty gross. Yeah. But this is fascinating stuff. So if this doesn't, I'm going to let you do the body one. Okay. Now that one's not a two-parter because it already tells you the constant. So you don't have to do all that work at the beginning to find the constant. So yay. All right. This one's about pizza. So everyone loves it because it's about pizza. Let's talk about this one. I love this question. Okay. Bears. Bears in wildlife or anything in wildlife, guys. Now, if you had an island of bears and just nothing as far as a predator that would kill a bear on this island, right? And you just let bears do what bears do. At some point, the population is going to flatten out, right? There's only so many resources and space for the bears to live on. So nature will take its course and they will either kill each other for the resources or they will just stop producing at an intense rate. That's, yes. Well, nature will always take its course, right?
And that's why we also can't kill animals to kill humans.
Oh my gosh, you got really deep there. Okay. So, this formula, this is called logistic growth. And we're going to do a lot of this tomorrow. But basically what happens with logistic growth is you're going to want a picture of what this looks like. So could y'all go to Y1 and type this function into your calculator? But what you have to be very careful about when you type it is that you put that whole denominator in parentheses, okay? So type carefully. I'm going to go show you my calculator.
Looks like Newton just decided to figure it out just because.
Probably not. He's a smart dude. I don't want to discredit Newton. He probably did most of it on his own, right?
No, it looks like he just wanted to do it because, though.
Oh.
It wasn't like,
like
he was
yeah.
like, I want to, it was, I want to know how long it's going to take for my cake to get here. It's not really important. But,
But it was important to him. Maybe he really did like a nice indirectly cooled piece of mutton or something. I don't know. Okay, so you'll notice in Y2, I also have a 50. That's a follow-up question coming on this question. So go ahead and type that in while you're there. But we would have to adjust our window in order to see what's really going on here, guys. So if you go to window, and X represents time, so I just kind of willy-nilly chose 100 to end my time because I wasn't really sure what these bears were doing, but I gave them 100 years to figure it out, okay? So 0 to 100, and then I actually cheated big time and I did zoom fit, which is fine, but I changed the Y's to that. Let's look at that graph for a minute. So the blue line represents the population of the bears. What do you notice happens?
It flatlines.
It flatlines essentially, and that's what logistic growth will look like, okay? So for the questions in your notes where it's like, what's the population at 0, 3, 10, 30 years? Since I have a graph right now, I could just start typing like 0, 10, and so on and so on. And then they want to know when the bear population reaches 50, and that would be an intersection. So I would just quickly do an intersection. So it's about 4.45 years it's going to take to get to that point in population. And then as far as like, well, where does it flatten out? This is the best news for you. What is that number right there? Well, that number right there, that top part where it flattens out, is always the numerator of your formula for logistic growth. So the bears cannot, basically the population is going to flatten out at 300. They're going to run out of resources and space and they can't produce anymore. So essentially they'll kill each other until it equilibriums. Yeah, pretty much. And maybe nature will really take its course and there'll be a virus that comes through and kills them. That happens sometimes in ecological. Well, not the plague. Jeez, you're so dark today, Daniel. Okay.
I know.
I'm going to jot down some answers here for the slides. You guys, worksheet 10 and 11 for homework.